Today's lesson is on the strengths of acids and bases. So we're going to see that not all of them are equal in terms of what happens when we put them in water. We'll see what the difference is. Okay, so not all acids are equal. So for instance here, HCl, this is hydrochloric acid, which you should be able to name. This one we may not have seen the name of yet, CH3COOH. If we remove off this last H here for a second, we'd realize this is the acetate ion. And if we change that based on our naming rules, this would be called acetic acid, which you might know better as vinegar. It's the thing that gives vinegar its very distinct smell. So what happens when I put both of these in water? Well, HCl, hydrochloric acid, is what forms. It comes from hydrogen chloride gas. But what happens is you get 100% of it breaking apart. All of the HCl becomes H plus and Cl minus. So this arrow only points in the forward direction because we get 100% dissociation is what this is called. This CH3COOH, the acetic acid, does not do that. It is less than 100%. In fact, it's probably more like 1% realistically here. Of this stuff breaks apart into hydrogen ions and acetate ions. It's still an acid because it does still produce some hydrogen ions, but not nearly at the rate that this first one does, where 100% of it comes apart. Here, it's like, I don't know, 1% or so of this breaks apart. So when you put these into water, strong acids, and HCl is an example of a strong acids dissociate completely into ions. Okay, so we get 100% dissociation. Everything breaks apart. All the HCl turns into hydrogen ions and chloride ions. When put into water, weak acids, so this acetic acid, as an example, do not completely dissociate into ions. Some of it remains as the molecule or compound, so only some of this comes apart. We know some of it does, though, because of the hydrogen ion that forms. If we tested this, it would show up acidic. If this didn't come apart, it would appear neutral in solution. Okay, so a strong acid is an acid that ionizes completely in water. So that means we draw an arrow that only points in the forward direction, which means that we get 100% of this breaking apart. The list of strong acids, you must memorize this list. It's not a very long list, okay, so make sure you know it. HCl, HBr, HI, HNO3, HClO4, we're not going to worry about this one, and H2SO4. Okay, there are more than this, but these are the most basic ones. The other strong acids that would get put on this list are a little bit more complicated, so we're going to keep it pretty straightforward. HCl, right, we're just going to go through and name these. Hydrochloric acid, HBr, hydrobromic, right, these are binary acids, so this is hydrobromic. HI, it's kind of the weird sounding one, hydroiodic acid. HNO3, so now we're talking oxy acids, it's nitrate ions, so this is nitric acid. HClO4 comes from a perchlorate ion, so this is perchloric acid. And H2SO4 comes from a sulfate ion, and this one actually breaks the naming rules. So it comes from a sulfate ion, so you would think it might be sulfic acid. That's not actually what this is. You've probably heard of this before. This is sulfuric acid, is H2SO4. So it doesn't follow your standard naming rules, okay? Where we just changed the 8 to ic. We added in this UR, so it's sulfuric acid. All of these will completely dissociate into hydrogen ions and their respective anions. So if you take, HNO3 and you put it into water, 100% of it comes apart, so we only draw an arrow pointing in the forward direction into hydrogen ions, right, that, and the respective anion, a nitrate ion, NO3, kind of hard to read that, okay? They will all do this. 100% of it dissociates. Okay, weak acids. Any acid not considered strong is a weak acid. So if you memorize the list of strong acids, anything else that, say, starts with H, okay, that was not on the previous page is considered weak. So there's only like 6 strong acids that we need to know, and we're going to consider every other option that I'm going to give you weak. HF, this is one that often tricks kids because they assume that since it's one of the ones bonded with a halogen, fluorine, that it would be strong. HF is a weak acid. This is hydrofluoric acid. Make no mistake, this stuff is still really, really nasty. It's just not considered strong. The term strong and weak doesn't mean that, a weak acid isn't dangerous. Really, the danger in all of these things is in how concentrated they are, not whether they're considered strong or weak. Strong or weak is simply just a designation to tell, does it dissociate completely or not. The second one we already saw, right? We saw this one just a few minutes ago. This is acetic acid, right? That's vinegar. H2S, that's being hydrogen sulfide. We're not going to worry about naming that one because we're not going to see that again. H2CO3, though, let me fix this 3 on here real quick. This one we do want to name. The CO3 ion is a carbonate ion. This is an oxy acid, so the carbonate changes to ic. This is carbonic acid. Go check it out. This is in soda. So if you go look on the side of like a Coca-Cola can, it'll say carbonic acid on it. HClO, that is a hypochlorite ion, right? This is a oxy acid, so this would be hypochlorous. We kept the hypo as part of it, hypochlorous acid. H3PO4, this is another one that breaks the rules. That's a phosphate ion. This is not phosphoric acid, right? Okay, which is what you might think based on how that works. This is phosphoric acid. This is also in sodas. So if you go look on the side of a can of Coca-Cola, it should say phosphoric acid, so it's got some H3PO4 in it. These do not completely dissociate into ions. So if we take HF as an example here, we do not get 100% dissociation. In fact, all of these are really 10% or less. 10% is kind of the extreme in terms of a weak acid. Most of them are significantly less dissociation than that. HF would break apart into hydrogen ions and fluoride ions. Notice here, unlike before, I have an arrow pointing in the forward direction and an arrow pointing in the reverse direction, indicating that this reaction does occur in both directions. Most of it stays in this form. Okay, so strong bases now is a base that dissociates entirely into metal ions and hydroxide ions. That means it 100% dissociates and the arrow only points in the forward direction. An example here of a strong base, NaOH, sodium hydroxide, is 100% going to dissociate into sodium ions and hydroxide ions in water. Will look just like that. Here's the list of strong bases. You need to, just like the list of strong acids, know these. Now, the nice thing about this, okay, we have NaOH, LiOH, KOH, RbOH, CSOH, okay? This first bit here, all right, those are all 1A metals plus a hydroxide ion, okay? And the ones here are all 2A metals plus hydroxide. So you need to know this list. These dissociate completely. Okay, so if we have CSOH, we put it into water, we get 100% of it turning into cesium ions, excuse the bell there, and hydroxide ions, like that. Okay, so a weak base is a base that only ionizes partially in water. So we're going to have less than 100% dissociation. So I'm going to go ahead and fix this one up here. Okay, we got CH3NH2, and if we put that into water, H2O, let's see here, okay, we don't get 100% dissociation. Okay, we only get this partial dissociation. It's going to be less than 100%. It's going to be probably realistically less than 1% or 2, but we do know that it does occur, because if we tested this substance in water, it would show up as being basic, CH3NH3. So we get a positively charged ion here, the CH3NH3 with a positive charge ion, and a hydroxide ion, okay, as well. So even though this doesn't have hydroxide in it, it does produce hydroxide, so that's why we do consider this a base. But this is less than 100% dissociation. Some other bases that are out there, we've already seen some of these. Okay, I'll go ahead and try to write these correctly for you. We have NH3, we have CH3, NH2. Anything that's got that NH3 or NH2 group on it is going to be considered a base. And you don't really need to worry about naming these. They get a little bit more complicated here. This one's methylamine. I think this one's ethylamine. I think this one's benzylamine. But what you're looking for there is NH3 or NH2. The other thing to look for something that's considered a weak base is anything that contains a carbonate ion.